Thank you, Zoom, for telling me the recording is in progress. So welcome to, I think this is week 6 now. We are going to look at a slightly different way that the schools do it. The schools will now go into like macromolecules, where you have proteins, carbohydrates, plastics, that kind of thing. And then they revisit this topic again in term 3. I like to stack it back to back because it makes sense and it's fresh in your mind rather than having to come back to all this stuff when you learn about it. We talked about a class of macromolecules called the esters. And there is this process called esterification. Now, we will visit this process in a lot more detail and look at it at its industrial applications. The first 30% of Unit 4 is just learning organic chemistry. Eventually, we will start to look at industrial applications, building molecules, creating synthetic pathways for the creation of these molecules as well. But for this, this will actually be the last week of it. And then we will start to do your biomacromolecules, proteins, carbohydrates, fats. Then we'll look at plastics as well. I might do plastics first. Sometimes it makes sense to do it that way. But we'll see how I'm feeling. So if we have the esters. Anybody remember what an ester is and what functional group it is? There we go. What's an ester's functional group? Anyone can remember? Just what's involved. So normally we would have a carbon here. We then have carbon here, a double bonded oxygen. Oh, sorry, and then a carbon here, or kook. Have a think. How would we make one of these? Or what 2 organic molecules will we need to put in there to make this? Just by looking at this here. So, part of last year's assessment for this was actually, we need to create an ester from 2 basic molecules. So an alkane and an alkene. And what we need to do is add carboxylic acid, which is this bit, and an alcohol. If I can spell properly. So we add a carboxylic acid and an alcohol. The alcohol is this part here, this chain. Carboxylic acid is this, going this way. And creating these esters, we use esterification. Its applications in industry are creating biofuels. We use it to make soap. We can use it to make soap. So we're going to learn, we learned the simple reactions a couple of weeks ago, substitution, elimination. I've just started uploading the last 2 videos. I was slack in putting those up. I do apologize. So we are going to learn how to make these one of these from an alkane from an alkane and an alkene. So we're studying the process of esterification. And we want to create an ester from a carboxylic acid and an alcohol. But in the assessment, you're only given 2 basic alkanes, or an alkane and an alkene, if you really want. So we can make an alcohol 2 ways. Does anybody remember from their notes from a couple of weeks ago how we make an alcohol? Actually, there's 3 ways. But we'll look at 2. We can take an alkane, add hydrochloric acid. So we go from an alkene, which has so if we add HCl, it's going to reduce this double bond. And now we have hydrogen goes there, chlorine goes there. Now we have a halo alkane. So alkene plus HCl gives us a halo alkane. To go from a halo alkane to an alcohol, what's the alcohol's functional group? Anyone? So alcohol functional group, what's attached? If it makes you feel any better, this is as complicated as it gets. Thank you, Jacob. I assume that's Jacob. OH minus. So we add OH minus, we add sodium hydroxide, or better known as drain cleaner. What happens here is we want to replace the chlorine with our OH minus group. So we end up with now ethanol. So I would be certain that this question will be in the exam in some form. Whether it be a complex question, whether it be a multiple choice, I don't really know. But it's one of the whole points of learning everything we've learned up to this point, is this process. And I'll actually remind me to upload the slides when I send this as well. I have a really good slideshow for it. So alkene plus hydrochloric acid gives us a halo alkane. We add sodium hydroxide to our halo alkane. The OH group here, or sorry, the Cl group here, chlorine, is attacked by the OH group. OH kicks the chlorine off. We now have ethanol. So we take, now making the carboxylic acid is not actually something we've gone through yet. Oh, pardon me. So, we make our alcohol, alkene, haloalkane to alcohol. There's another way to make it. That is just one step, but it's expensive. The whole point of this industrial chemistry unit is to take chemistry away from pure science and actually look at producing something. It needs to be made cheaply, it needs to be made safely, and we need to make lots of it, rather than just learning about science. There's a lot more to science, especially in this stuff in industry. A lot more money to be made in industry doing science. So the second pathway, again, we start with our alkene. We add, I don't know if I remember this one, we add water, we add hydrogen phosphate, and we heat it to 300 degrees Celsius. This is actually called, how terrible the lighting is there, I need a different light. It's called steam reforming. It's actually how you make hydrogen gas from methanol as well. Sorry, methane, not methanol. So what happens is the H2O, when it's heated with the catalyst, becomes OH minus and H plus. So we get rid of this double bond. Hydrogen goes on this side. And we end up with ethanol. That's the simplest way to make an alcohol. An alkene plus water, hydrogen phosphate, and 300 degrees Celsius. So that's how we get to ethanol. What we also need to add is a carboxylic acid. This is a bit of a process. So we start with propane. And if we remember, the carboxylic acid functional group is we need to create an alcohol group or a hydroxyl group and a carbonyl. Let's get some terminology happening. So that's what a carboxylic acid functional group is. We have a carbonyl group and a carboxyl group. Hydroxyl, not carboxyl. Hydroxyl group, sorry. Okay. So now that we remember what the carboxylic acid group is, we go propane to, we'll need to create a haloalkane. So any of these reactions, most of the time, we're going to haloalkane and then substitute again. So if we add chlorine, so this is partly a little bit of revision, testing your knowledge as well. So chlorine plus UV light, what would that give us? if it's a substitution reaction with an alkane. Move my fat head out of the way. So what would happen? UV light will break the bonds between carbon and hydrogen. Chlorine is more reactive than hydrogen. It will take its place. So, any guesses as to what this one will be called? What its IUPAC name would be? So, we name the parent chain. Still propane. We have chlorine, so we call it chloro, and it's coming off the first carbon. So it will be 1-chloropropane. So now we need to make the alcohol part, or the hydroxyl part, of our carboxylic acid. So we add sodium hydroxide to our haloalkane. So the hydroxyl group attacks the chlorine, kicks the chlorine off. We end up with an OH group in its place. Something that enraged me last year. When you're talking about organic chemistry, there's always going to be something else left over. So if we've reacted sodium hydroxide and 1-chloropropane, what we're also going to have left is Na and chlorine. So not only do we have our alcohol, but we also have salt as well. So now we have, again, let's name it. Here. 1, because it's what kind of alcohol? So primary, secondary, or tertiary? So 1, it's propan, because it's 3 carbons. It's coming off the first carbon, and then we call it out. Propan 1-ol, or 1-propanol. IUPAC naming is propan 1. Now, what we need to do is get rid of this hydrogen and replace it with a carboxyl group. And we can do that. We did some when we looked at the primary, secondary, and tertiary alcohols, where we have an oxidizing agent. What the oxidizing agent does is it gets rid of the H, gets rid of this H, and creates the double bonded oxygen. So common one. It's a 3+ molecule, not 1+. And what this does, because it has a 3+ charge, it wants electrons. So it will attack the double bonds and attack the single bonds and harvest electrons. So what we'd end up with is no hydrogens on the ends, but a double bonded oxygen and OH. Anyone want to name that molecule that we have here? So Cr2O7 3+. My HD screaming computer is out of action at the moment. It needs to be taken apart. Apparently this is this computer's version of HD. So any ideas what this one would be called? So I'm going to give everyone, no watches, dead. So I'm going to give everyone till, yeah. Propanoic acid. We know the functional group is carboxylic acid, 1, 2, 3 carbons, propanoic acid. So we're about halfway to our goal of making our ester. I'm no good at doing a reverse camera. So we've now created our propanoic acid and our ethanol from our simple hydrocarbons. Alcohol, we use ethene. Here we use propane. So we've got our carboxylic acid, which is propanoic acid. Then we add our ethanol. So esterification is a weird process. And I'm going to actually draw the OH group on this side. And I want everyone to draw this so that we can actually visualize what's happening. So we've got a minute to draw it. My fat head of the way. So what happens is the chains join here at the OH groups. And what happens is we actually lose this OH group and this hydrogen. So there's 2 hydrogen and 1 oxygen. That will make water. But what it will also do is produce a bond between the oxygen and the carbon. And this is a reaction you need to get used to, understanding, and it's a condensation. So what we actually end up with is a molecule that looks like this. We've got, on the left, we've got our carboxylic acid. Then we have what's left of our alcohol over this side. So now we're left with this molecule. This is our ester. Everybody, let everyone a second to draw that molecule. And we name it unlike any of the other organic compounds. The name it like the ester molecule is this part. I need to get rid of the dog because 3 seconds. So the ester part we name O8 on the end. Got 3 carbons. So we call it propanoate. And this is just an alkyl side chain. So what if this is an alkyl side chain here? What do we call it? So this molecule will be called ethyl because you've got 2 carbon alkyl side chain and propanoate for the left-hand side. On the left-hand side of this oxygen, you name O8. How many carbons are on this side is O8. Carbons on this side, alkyl side chain. All right, I'm not going to go any further into that because we'll go into esterification when we look at biofuels and biodiesels, that kind of thing. That's for term 3. All right, what I want to do now, go through some review questions for everything we've done. As of next week, we start on our polymers, carbohydrates, proteins, amino acids, blah, blah, blah. So what would this molecule be called? I'm going to fire these out super fast. We're going to do, I'm going to do 6 weeks, 7 weeks of content in 20 minutes. What would we call this? Propane, correct? Got that? So this would be propanamine. And would it be a primary, tertiary, or secondary amine? Carbon that the nitrogen is directly attached to is attached to one other carbon only. So it will be a primary amine. What kind of intermolecular forces would we see in an amine? So we have nitrogen attached to hydrogen, so we would have hydrogen bonds. Would this amine dissolve in water? Well, there's 2 hydrogen binding sites there, so it would very soluble in water. So, how would we make this? What base molecule plus what would we need to make this amine? So to make the amine or the NH2 group, we need ammonia. Or NH3. We need a haloalkane. So we've got a haloalkane, we add ammonia, we get a substitution reaction, not here. Pretend that the bromine's over here. We get a substitution reaction here. So we add ammonia to our haloalkane. We get a substitution reaction at the bromine, which produces our amine. We'd also have one hydrogen plus the bromine. So the full answer to that question in an exam is this is the reaction required. We would also need to add UV light. So UV light, bromine, NH3, it's getting kind of messy now, sorry. So we add UV light and ammonia to our haloalkane, and it gives us an amine and hydrobromic acid. All right, so let's start with them. Do the same thing again, but we'll do it without alcohol. So is this a primary, secondary, or tertiary alcohol? Primary, correct. Would it be soluble in water? Yes, soluble in water, because we have hydrogen bonds. What? Oh, I just said what kind of bonds we have. Smooth. How would we name that? So it's ol for an alcohol, propan. So we would call it 1-propanol. I'm going to give everyone a minute to think about this. How would we make it? We just did it. So hopefully you're writing it down. So we start with, I'm going to tell the easy way. One of the easy ways we can make it. We could make it from propene or proguanine. We could just do our steam reforming. We add water, H3, and 300 degrees. And we will end up with propanol or 1-propanol. Right, I'm going to do one more molecule. This one's going to be really annoying just to finish. So, what on earth is this? Actually, I'm going to change it because I just realized I made that way more complicated than I wanted to. What on earth do we have here? Close, Jacob. But what do we have there? So here we have an alkyl side chain. So I wasn't following the octet rule there. One too many hydrogens. And then we have double bond. Which one takes precedence in the naming? The double bond takes precedence. So we call that propanine. But we have a methyl side chain coming off the second carbon. And I'm going to set a homework task now. Task for homework is to name that molecule. And I will see you guys next week, where we'll get into the nitty-gritty of actually learning stuff rather than just going at what we've been learning, but just learning the basics. So everyone to name that for homework. And I will see you guys next week.